We will now discuss the case of motion along a circle, circular motion. Now, how can we make things move along a circle? Now, imagine that there is a student running, say, from one end of the room to the other, and I get hold of him by the hand. What will happen? That student will go around me in circular motion. You see, our old moon was going away for a stroll very, very long time ago, and it got caught by the Earth's gravitational field, and ever since that time the moon has been going round along a circle perpetually. Now, what is it that is necessary to make an object to move in a circle? The student who was running away, I did not catch him. He would have gone away in the same line, along the same straight line. Now, when I caught hold of him, I apply a force on him towards me, and he goes around in a circle. Now, as he goes around in a circle, if I leave him, he will go along the tangent of the circle. As long as he stays in a circle, the force that I applied will be there. In other words, an object can be made to move in a circle only if there is a force acting towards the center of that circle. When the moon goes around the earth, the force that keeps it going around the earth is the gravitational force between the moon and the earth. The moment the earth says, "Moon, I'm not going to pull you today," the moon is going to go away. Well, you must understand this concept very well. An object can be kept moving along a circle only if there is a force that is directed towards the center of the circle. Now, here I have a ball, I have a string tied to it, and I'm holding at one end. I'm going to give a ball a velocity at right angles to the table, in the direction I'm pointing. Now, look what happens when the ball is given a velocity that way. Now, what is the motion of the ball? Watch it again. I'm giving the ball a velocity in this direction, but where does the ball go? Now, it goes along a circle. Why? It goes along the circle because, look at that. It goes along the circle because I apply a force towards the center of the circle. Now, it is that force that keeps it moving along the circle. Now, as it moves, I leave it, it will go along the tangent. Now, this is an important aspect of circular motion. We will now discuss some of the terms that we use in connection with circular motion. Consider an object at the point A on the line OA. Now, it moves along the arc of a circle of radius OA. There, the object moves along the arc of a circle of radius OA to position B. Well, that is circular motion. Is that right? Now, OB equal to OA is the same as the radius of the circle. The line OB makes an angle theta with the original direction OA. So, when the object moved from A to B, the radius of that circle rotated through an angle theta. Now, when the object moves from A to B along the circular path, look at that, the length of the path taken by the object is the length of the arc AB. and during that time the radius rotated through an angle theta from position OA to position OB. The angle theta is called the angular displacement of the object. So, when we talk about linear motion, displacement can be in the x direction, y direction, or in any arbitrary direction. We have a linear displacement in linear motion. When you consider the circular motion, the displacement can be measured in terms of the angle described by the radius. So the angle theta is called the angular displacement of the object in circular motion. Now tell me, when the object completes one circle, what is the angular displacement? The angular displacement for one complete circle is 2 pi radians. If the object goes around twice, the angular displacement is 4 pi radians, and so on. It is a very convenient way of keeping track of the motion of a circle or motion of an object along a circle by measuring its angular displacement. Now, if this angle theta is described in a time t, then the rate at which the angle described can be written as theta over t. Now, the rate at which the displacement occurs is called velocity. Is that right? Now, if the rate at which the linear displacement occurs is called the linear displacement, then the rate at which an angular displacement occurs can be called angular velocity. So, an object that goes around a circle has an angular velocity. The rate of change of angular displacement of an object in circular motion is called its angular velocity, and we will represent that by the letter omega. The Greek letter omega represents angular velocity. And omega equal to theta over t, or delta theta over delta t. The change in the angular displacement divided by the change in time is angular velocity. Now, what is the unit of angular velocity? The angle described is measured in radians. So, the unit of angular velocity is radian per second. Now, remember, our units are determined by the dimensions, length, mass, and time. Now, radian is a dimensionless quantity. It has no dimension. Therefore, when you write the unit, normally radian will not appear in the calculation. So, what is the unit for omega? It can be called per second. Although we write it radian per second, in calculations it will only appear as per second. But whenever we write the unit for omega, we will write it as radian per second. So, an object moving along a circle has an angular displacement and an angular velocity. Okay. What is the relation between angular velocity and the linear speed? Well, if an object is moving around the circumference of a circle, it has a linear speed. What is speed? The rate at which the distance is covered. Now tell me, when the object goes around the circle once, what is the distance it covers? When the object goes around the circle once, the distance it covers is the circumference of the circle. That will be 2 pi r. Is that right? Okay. Now, the length of the path S of the object is the distance measured from A to B. Now, what is the distance measured from A to B? That is the length of the arc. Now, can you tell me, what is the length of the arc in terms of the radius and the angle theta? A very simple relation I'm sure you must have done in your trigonometry class. Now, that says the length of the arc subtending an angle theta at the center. Now let me see if I can illustrate that. If an arc of a circle subtends an angle theta at the center, then the length of the arc S will be equal to, if the radius is R, then S will be equal to R theta. And this is an important result that we will be using at many places in physics. If the length of the arc of a circle subtends an angle theta at the center, then that length of the arc equal to radius times the angle theta. Well, tell me, what is the formula for the circumference of a circle? I'm sure most of you know. The circumference of a circle is 2 pi times the radius. Why is it 2 pi times the radius? Because when the circle is a full circle, the angle of the full circle, that theta is 2 pi. Then the length of the arc will be the circumference of the circle. So the circumference of a circle is this length S when the angle theta is 2 pi. So that will be 2 pi multiplied by R. Okay. So the linear speed of the object along this path, what is the linear speed of the object along this path? Will be the distance divided by the time. So if V is the linear speed, I can write V equal to S over T meter per second. The distance covered divided by the time taken. Simple concept. But as I just showed it to you, the distance S equal to R times theta. I have used lowercase r. Remember, R is the length of OA or the length of OB. So S equal to R times theta. Let's replace this S by R theta. What does then V equal to? V equal to, in place of S, I wrote R theta. So V equal to R theta divided by T. And that can be written as R times theta over T. Now what is this quantity? The rate at which the angle is being described is called the angular velocity. So this can be now written as R omega. So what is the relation between linear speed and angular velocity of an object in circular motion? If an object is moving around a circle, the object has a linear speed at any given time and also an angular velocity, the rate at which the angle is being described. They are related by the relation V equal to R omega. A very important relation. I want you to remember that. Now I tell you many times, I want you to remember these relations. But do you really do that? I will ask you this several times in the course. And if you're doing physics 2, I will ask you that there also. Because this is such an important relation. So V equal to R omega gives a relation between linear speed and angular velocity.